Hello everyone. This is second presentation on ML. In the first PPT, we got a brief introduction to this exciting field of ML. In this talk, we will look at some of the very basic and most commonly used algorithms. And of course, this is not an attempt to touch upon each and every details, but still we will try to get a gist of the core ideas behind these algorithms. And I will start my presentation with a quick revision to our previous talk. So in the last presentation, we first looked at some of the very popular applications of ML, and then we saw how the ML is different from traditional programming. What we saw is in the traditional programming, we first construct some rules, and then we supply the data to our program to get our desired answers. And we also looked at this a simple program where the program takes any integer number as an input and then returns square of the number as an output. Whereas in machine learning, the approach is kind of reversed. So we have some data and the answer that maps to the data. So machine learning, what machine learning does is it figures out the rules which will map this data to the desired answer. So suppose we want to do the same job that we have done earlier in case of traditional programming. So that is the finding out the square of a given number. So what we would do is we would supply some numbers and their corresponding squared value to our program, and then program will figure out what rules the program should apply to this data to generate this kind of output. So essentially, from the definition perspective, ML is a field of study that gives computers the ability to learn without being explicitly programmed. So, and after that, we also looked at the three different classes of machine learning algorithms, like supervised learning, unsupervised learning, and reinforcement learning. And in supervised learning, there are two basically kind of algorithms we have: logistic regression and classification. And unsupervised learning, we have clustering, dimensionality, reduction, like that. In the regression analysis, what we typically do is we have some variables and we try to okay, we will look at this later. So for a sample problem, we looked at the linear regression problem, which is nothing but a curve fitting problem. So suppose we have this kind of data where we have some x and x variable, and there is some y variable which is corresponding to x variable. So for every x point, x value, we have a corresponding y value. And what we want is we want computer to train a model in such a way that if we have some x for which we do not have any x value, suppose for x equals to 12, we do not have any data point which can give us the value of y, the model should be able to give us the y value. So if we want to train a model like this, what we can do is we can fit a straight line to this curve, and if we have this straight line, equation of that straight line that represents these data points in a best possible way, then we can put a x value there and we will get a corresponding y value. So to do this, we have seen that how can we apply the method of least square and then associate it with gradient descent approach to figure out the optimum value of m. So, and then to do that, we started with a random value of m. So to corresponding to this random value of m, there can be some random straight line like this, and then we expressed the error value as this following, like the y predicted minus y ground truth. So in this case, suppose here is a data point. So in this case, the ground truth is this data point, and the predicted value would lie somewhere like this. So the difference between these two points would be the error, and then we did the same. We find out the error for all these data points, and then we find the sum of the square of these errors. And what our objective is to minimize this j, that is the sum of the square of these errors. Here the e is that is the y predicted minus y ground truth is called as loss function, and summation of the square of these errors is called as cost function. And then we applied the gradient descent approach to find out the optimum value of m. So how did we do that? We started with this random value of m, which is 0.3, and then we finded out the gradient of this cost function j, which is nothing but sum of the square of these errors, and we finded out the gradient of this j at this point, and then we multiplied it with some learning rate alpha, and then we updated this m in such a way that we move towards the local minima, which is also the global minima in this case, towards such that we move towards the global minima of this problem. So when we reach to the minima, that is where the gradient of this cost function with respect to m becomes 0, we say that okay, this is the point, this is the value of m for which our the j is minimum. That means our error is minimum. So by doing this, by doing this procedure, we were able to move this a random initial guess to our line, which is the best possible fit for these data points. So in this talk, before we move further, I'll introduce you to some terminology. So typically we have some data, and in this we have columns like this, and we call these columns as attributes or feature. In case of supervised learning, we try to express this target attribute or target variable in terms of the linear or non-linear combination of these features, or sometimes called as attributes. And then each row of this data is called as instance or observation or data point, and the expression with which we express the target variable in terms of the linear or non-linear combination of these attributes or feature is called as hypothesis. And here the theta naught, theta 1, theta 2, theta 3 are some parameters for which our objective is to find out the optimum value of these parameters, so that this hypothesis is able to predict the y value accurately. And also you will sometimes may encounter the term like hyperparameters. So these hyperparameters are higher level properties of a model, like learning rate we have seen, depth of decision tree, and number of layers in any neural network. So how you can differentiate between these two terms like parameter and hyperparameter is that parameter is something that computer try to optimize by itself, and the hyperparameter are something that that we as a programmer or we as an end user try to we as an end user supply to the model even before the model is trained. So in case of like this the gradient descent approach, we fix the learning rate, that which is a kind of a tiny step that is taken in each and every iteration of the optimization. So these are called as hyperparameters. And another term that you may encounter is cross validation. It is a technique to compare performance of ML algorithms. So what we do is, in any ML algorithm, we first start with a data set, and we divide the data set into two categories: training data set and the test data set. So our objective is to first train our model on this training data set, and then test our trained model with this rest of this with this rest of the data. Typically what we do is we keep 75% of data as a training data, and we use 25% of the data as test data. But this is not any hard and fast rules, and the proportion that with which we divide this training data and test data is typically depends upon the size of the data we have. So first we keep some portion of data as a test data, and train our model on the rest of the data. And on the second iteration, what we do is we repeat the same process, but this time the different part of this data is used at test data, and the rest of the part is used at training data. And we again repeat this process by changing the test data and training data, and we repeat this process. And in the end, all the results from these iterations are compiled to evaluate the performance of the algorithm. So suppose we have divided our test data in this fashion. So we will have four iterations. So we call it as a four-fold cross validation. So if we have k different iterations, then we call it as a k-fold cross validation. And the next term that is quite important is bias and variance trade-off. So any kind of prediction error that we see in any a model can be attributed to two different categories. First is bias and the second is variance. So bias is an error due to simplification or approximation in the model, whereas variance is the amount that the estimate of the target function will change if we use different training data. So let's consider it with another example. So suppose we have some kind of data like this, and we want to categorize these data points in two different categories, like blue dots and red dots. So one possible way is to use a decision boundary like this straight line. So if we use a decision boundary like straight line, we will never be able to accurately classify this kind of data. So all these blue dots which are here will be definitely classified as a misclassification. So this is not because this is definitely because of the model that we are using is very simple. It is not it is very approximate. It is not able to properly classify this kind of data. And whereas in this category, in this picture, what we are seeing is the best possible decision boundary we can have. So here we have some kind of parabola type of structure, and which classify all these points as red points and all these outside data points as blue points. It also takes into account these outliers, which would be classified as a wrong classification. But this is okay. This is what we need to do. But if your model is too accurate, or you can say too complicated, then the model may try to incorporate these outliers. So if this is the case, then we will again have a wrong model, which will classify the new data point in a wrong fashion or misclassification. So this kind of fit is called as underfitting. It is just right, and this is overfitting. So this is because of simplification of models. So this is error due to bias, and this is due to the overfitting. So if we change the in training data set, so these outliers may fit maybe find it out somewhere else, or somewhere here. So in that case, this model will change, and we will see a different kind of models, and the new data points will be classified in a different way. So this kind of error is called as error due to variance, and it is due to overfitting. So to figure out what we are doing is, in this kind of data set, we see a high training error, and we also see a high error during testing phase. And whereas in this case, we will see a very low error during the training phase, but we will see a high error in the testing phase. So the linear regression which we saw earlier is not the only algorithm we have. There are a lot more other algorithms too. Here is a list of categories in which we can categorize these algorithms, or these algorithms can be grouped together. Each of these categories contains a list of algorithms, and in this talk we will look at some of these algorithms, especially those are highlighted in bold face. Here are other algorithms from other categories. So first of all, we will look at the logistic regression. It is the first algorithm that we are going to discuss today. First of all, as the term suggests, it is not a regression algorithm, it is a classification algorithm rather than a regression algorithm. So any mathematical function that have a characteristic S shape are called as sigmoid functions. So for example, in this function you can see a S shape. So all those functions which have this S shape are called as sigmoid functions. Typical examples are logistic functions, hyperbolic tan h, hyperbolic tan function, or error functions. The equation for this logistic function is given by this. So this curve represents this equation. So whenever we use logistic function to predict the probability that the dependent variable will fall into one of the two categories, we call it as a logistic regression. We can do it because if you look at this curve, it range from y value range from 0 to 1, and we can, and you know that probability also range from 0 to 1, so we can make use of this type of curve, so that if the probability, if the y value is greater than 0.5, so we can call that okay, the input variable, input data point will be belonging to some category A, and if the y value or the fx value is less than 0.5, we can attribute or we can classify this new incoming variable as the second category. So how do we do it? So technically, from the implementation perspective, here is the structure that how we do it. So here we have some 3 or 4 columns, where in the first 3 columns we have input variables, and the y is target variable that we want to predict. So first of all, what we do is we form a hypothesis function. So what we do is we try to express or try to form a linear or maybe non-linear combination of these input variables, like as you can see here. And again, theta naught, theta 1, theta 2, theta 3 are the parameters that we want to optimize. And then we express our hypothesis function like this, which is a logistic function. And then we express the cost function like this, which j as a function of theta. And we have chosen this function so that the resulting curve or resulting function j do not have any more than one local minima. So we want to have only one local minima, which is also global minima. So the choice of this cost function is resulting from that perspective. And then we apply gradient descent approach to find out the optimum value of theta naught, theta 1, theta 2, and theta 3. This is how the logistic regression works. And although I have explained this the implementation in this implementation for this logistic regression, but I will skip it for the later algorithms that we are going to discuss today. So the next algorithm is k nearest neighbor. I find it very simple and very intuitive. So it is again a supervised learning algorithm, and the key idea is that the value or the class of the data point is determined then data points around it. So suppose we have a data point here, so and we want to know that okay, from which class this data point will belong. Will it belong to either this class, which is represented by the green points, or the yellow points, or these blue points? So what we will do is we will look at some number of nearest neighbors. So in this case, I have encircled 4 nearest neighbors, and if we want to classify this data point, then what we will do is we will look at the class of these nearest data points, and we will decide the class of this new data point by majority voting principle. So suppose 4 out of these 3 points belong to the blue class, then we will say that okay, by majority this new data point will also have the blue class. And suppose we want to use this algorithm for regression analysis. What we would do is we would take again some 4 or 5 data points which are near to you, which are its neighbors, and then we will take average by value, and we will assign that average value to this new data point. And the number which we choose for like 4 or 5 is, we call it as a k value, and that's where the algorithm gets its name, k nearest neighbor. Again, we want to use an optimal value of k. If the k is too small, it will be an overfitted model, and if the k is too large, it will be an underfitted model. So the next algorithm we are going to discuss today is support vector machine. It is a classification algorithm, and as you know that classification algorithms requires a decision boundary, sometimes also called as hyperplane. So suppose we want to classify these data points in two different categories. First is man and second is woman. What we need is we need a decision boundary which can classify these data points. Suppose if a new data point is here which is right to the decision boundary, so we will classify it as man, and if the data point is here we can easily classify it as woman. But this is not the only possible choice we have for as a decision boundary. We can have multiple choices. Like this is also this is also a possible choice for the decision boundary. So the question is, how do we choose the best possible decision boundary? So the SVM is a algorithm that finds the best possible choice for these hyperplanes. How do we do it? It essentially given a set of points for points of two types in n-dimensional space, SVM generates an n-1 dimensional hyperplane to separate those points into two groups. So okay. So suppose we will take understand the support vector machine by taking one example. Suppose we have a new data point which is shown here in a circle. We want to classify it. We want to know if whether this point would lie in this class or in this class. So we have a multiple choices of decision boundaries, and we want to know the best possible decision boundary. So the question is, how do we find the best choice? So what we do is we draw two lines parallel to this our hyperplane or this line in such a way that each of these lines touches nearest possible neighbors. So this parallel line touches this neighbor, and this line touches this data point, and we choose those lines as a best possible choice for our decision boundary, which gives us the maximum space between these two lines. So if I define the terminology, these two data points which are closest to these to which these dashed line touches are called as support vectors, and this blue line shown here is called as hyperplane, and the distance between these two lines is called as distance margin, and this line is called as d minus, and this line is called as d plus. But this is not always the case that we can easily construct a decision boundary. For example, our data looks like this. So we cannot say that okay, our decision boundary is as shown in this as shown by this blue point. We cannot say that okay, all these new points for which the x would be less than 6, we call them as a black data point, and for all those x for which the x is greater than 6, we would call this as a we would classify in the white category. This is not how we can do it. We cannot also place our decision boundary here, because this would also do a lot of misclassification. So how do we overcome this problem? What we do is we take this data, low dimension data, to a higher dimension data. So we take the x and we plot it against the square of x. So if we plot this x data against its square, then our data would look like this. Once our data is transformed in a higher dimensional space, then we can construct a hyperplane like this. Now this hyperplane would be able to classify this data accurately. So this mechanism in which we take our low dimensional data to higher dimensional data is known as kernels. Another example of kernel is as shown here. So suppose if we want to classify this data, then we will supply it to a kernel and we will translate. So yeah, to continue with, suppose if we want to classify this kind of data, and then we can take this data to a three-dimensional space, and then we would be able to classify this data accurately using a decision surface, which is a 2D plane. So essentially, the kernels are mathematical function for transforming data using some. So kernels are basically mathematical functions for transforming data using some linear algebra. So different SVM algorithms use different types of kernels options, and then as Akib suggested, we do not have only linear kernels, non-linear kernels, radial basis function, sigmoid, polynomial, and exponential. And we can also have decision boundary, which are of non-linear shape. So the next algorithm, which is very popular unsupervised learning algorithm, is k-means clustering algorithm. So in unsupervised learning, we do not have any labels for data. We just have data, and we want to see that whether can we group this kind of data in some groups. In this example, you can see that okay, two groups can be readily formed from this data, which are shown in this red circle and blue circle. So now how do we do how do we do it using computers? So one possible algorithm for this job is use k-means clustering algorithm. What we do is we start with uh, suppose in this case two centroids. We randomly place them anywhere in the feature space, and then we choose each of these points one by one. Suppose we have chosen this point, and then we measure the Euclidean distance from the Euclidean distance of these points from these centroids. And so, and then we look at the distance, then we compare these two distances. So whichever distance is less, we assign this data point to that category, and then we repeat this process for all kind of, okay, then if in this case we have assigned this data point as a red data point, or in from belonging to this class, and we repeat this process for all the data points, and we find that okay, these points are classified in this fashion. And then we again find out the centroid of the all these red points and centroid of all these blue points. So the centroids would be shifted depending upon, yeah, because of this allocation of the points in two classes, and then finding the new centroid of these points, we have we have got a new centroids. And then we will again repeat the same process. We will start with each and every point, and we will measure distance of each point with both of these centroids, and we will then reallocate these points to either one of these two classes. And by repeating this process to some iterations, we will be able to find we will be able to cluster these all these points in two different clusters. And then, and in this algorithms, the number of clusters we define before starting this algorithm is designated by the letter k, and that's why this algorithm got its name, k-means clustering algorithm. The next algorithm is dimensionality reduction. In this case, this was a 2D data, so we were easily able to visualize this data, that okay, and we will able to judge that okay, this data belongs to this data has two distinct clusters. But what if we have suppose 5 dimension, 10 dimension, or 1000 dimension data? How would we visualize that data then? So in that case, the dimensionality reduction comes to rescue. Again, one more reason why do we perform dimensionality reduction is, the more we have data, more memory it consumes, more computational cost it has, and more training time is needed. Again, there might be some cases when we have redundant features. For example, we asked some students to measure the radius, diameter, and mass of some spheres, and we want to establish a relation between these features and the mass of sphere. But in this case, you can easily see that okay, if the spheres are for these spheres, both of these parameters are not needed. We can easily take only one of these parameters, and we can establish our relation between the radius or diameter or the mass of the sphere. So there are several times when the same data is collected by different agencies, and those different agencies repeat the features. So there might be cases when we have redundant features, and we want to remove these redundant features before we perform our classification, regression, whatever we want to do. Again, there might be cases that okay, all those features are distinct, but most of the variation is happening only due to only some of the features, and only a little impact is made by some of the features. So we also want to get rid of those features. Again, there is another reason that we want to perform dimensionality reduction is the curse of dimensionality. So by increasing the dimension or increasing the features we have in our data, it is not always useful. If we increase the features we have, our accuracy of the model will increase up to a certain extent. But from that point onwards, if we further increase features, our performance of the model will reduce, because the sample density decreases exponentially with the increase of the dimensionality. Again, for the data visualization purpose, we also want to reduce the dimensionality of the data we have. So in this case, we want to remove those features and keep only the useful ones. Common algorithms that are used for this dimensionality reduction are these ones, and we will discuss only the principal component analysis, PCA. So here is a sample data set. For now, you can ignore this coordinate system which is shown in this black color. And now if you look at these yellow dots, if you look at these yellow dots, the variation in the data is happening due to both the change in x-axis and a change in y-axis. But if you somehow able to suppose if you want to develop a model to for this kind of data, you would need both a feature variable A and variable B. But somehow you are able to rotate the coordinate system, and then you can get two new variables like PC1 and PC2. In that case, you can see that most of the variation in the data is happening only due to this PC1 coordinate, and very less amount of variation in the data is happening due to PC2. So in this case, we can safely ignore this variable and keep only this single one variable. And if we do this, our 2D data would be actually reduced to 1D data. So this process is done by principal component analysis. So in original coordinates, variation is happening due to both variable A and variable B. But however, in the new coordinates, most of the variation is happening along the PC1, that is principal component 1, and very small variation is happening due to PC2. So using this analysis, we can reduce our variables or features that are included in our data. How do we exactly do this? So, what principal and component analysis exactly does is, suppose we have 10 variables, or you can say features or columns. What the PCA will do is, it will construct 10 other variables, which would be linear combination of the original variables. And it will also rank these newly constructed variables according to the extent that they affect the y value, that is our target value. So here is a sample diagram for this, and here suppose we have 10 principal components, and here is the percentage of explained variance in the target variable. So most of the variation in the target variable is happening due to first principal component, and the second most variation in the target variable is happening due to the second principal component, and so on. So if we want to say that we want to account for only those principal components for which, if we retain them, we will have, say, 90% of the variation. We can account for 90% of the variation in our desired y value. So we can do that. And so in this case, suppose we want to say that, okay, we want to account for only those principal components for which we will have total of 90% variation in the data. So in that case, suppose we can say we can remove all these 4 features, and we can retain only those 6 features. So with the help of principal component analysis, we can reduce the dimensionality of the data set. How do we exactly do it? So first of all, we compute the covariance matrix sigma. So the covariance between any two variables, or you can say any two columns of the data, is calculated using this formulation where xi minus where x bar is the mean of the data and y bar is the mean of y data, and xi is the individual data point, and then we perform this kind of mathematics, and then we sum all those data points, and then we divide it by the n, and then we get the covariance. And we do this process for all that suppose we have 10 variables, so we do it for all the every combination of these 10 variables. So in the end we will get a covariance matrix. Then we will find eigenvalues of this covariance matrix and sort them by their magnitude, and retain desired number of eigenvalues and find corresponding eigenvectors. So suppose we want to retain only those eigenvalues which have top 6 eigenvalues uh, when they are arranged in the magnitude. We can retain them and we can ignore rest of them. And for the retained eigenvalues we can find corresponding eigenvectors, and then we can these eigenvectors are called as principal components, and then we project our x data or input data on these principal components, and then we perform our whatever regression, classification or clustering analysis that we want to do. So the next algorithm that I want to discuss is decision tree. Sometimes we have data like this, and we want to construct a tree of decisions like this. We want to transform this kind of data in this kind of shape. So suppose let's take this example. Here it is data. In this data we have chest pain, whether the patient has good blood circulation or not, whether the patient has blocked arteries or not, and whether the patient has heart disease or not. So we want to make a certain kind of logical analysis, so that depending upon or by looking at these features we can decide whether the new encounter data point or the new encounter patient would have heart disease or not. So we can construct these kind of decision tree. Of course this look like a reverse tree, so that's why it got its name, decision tree. So if you look at this data like chest pain, yes, so we will see that whether the patient has chest pain, yes or no. If yes, then we will look at good blood circulation, whether the patient has good blood circulation or not. So this patient has good blood circulation, so yes, we will come in this category. And then we will see that whether that patient has blocked arteries or not. So this patient has blocked arteries, yes, so we will come yes. So this patient is quite likely to have heart disease. So this is what kind of structure we generate, and this kind of structure is called as decision tree. And from the nomenclature perspective, the first node of this decision tree is called as root node, and then all those nodes where we have one arrow as a input and two outgoing arrows, we call them as a decision node, and all those nodes where we have only incoming arrow and there is no outgoing arrow, we call them as a leaf nodes. So these are the final these are the final nodes where we see that what is the value of the target. Now the question is, how do we actually transform this kind of data into the decision tree? First of all, we look at each and every column. Now you can see that we cannot establish a direct one-to-one relation between each of using only one of these columns. So if suppose this has chest pain has no, and but heart disease is also no. This is yes, but this is yes, but for this the chest pain is yes, but heart disease is no. So we cannot establish a relation using only one of these features. So we call them as a impure attributes. So we construct a decision tree using an algorithm which filters out those attributes which have minimum impurity. For this purpose, we have typically two algorithms. First is using information gain, and second is Gini index. In this presentation, we will see how we use Gini index to construct this kind of decision tree. So first of all, we will look at, say, chest pain. We will pick one of these variables, and then we will see that if this is yes, and then for all those data points for which chest pain is yes, how many of these have heart disease no, and how many of these have heart disease yes. And for all those data points for which chest pain is yes but heart disease is no and heart disease yes, and we will make a list like this. So this branch corresponds to patients having chest pain yes, and this branch corresponds to patients having chest pain no. And out of those all those patients who have chest pain, 105 is found to be having chest 105 is found to have heart disease, and 39 were found to not have any heart disease, and the same goes here. So to find out the Gini index, we use this kind of formulation. This formulation is essentially this simplified in this line. So it is 1 minus probability of yes squared minus probability of no. So to find out the Gini index of this decision node, what we would do is 1 minus probability of this would be 105 divided by 105 plus 39, and this would be the probability of yes. And for this probability of no would be 39 divided by 105 plus 39. So if we do this kind of mathematics, then we would be able to find the Gini index for this decision tree. Similarly, we can find the Gini index for this decision node also. And once we have that, we find the weighted average of both of these partitions to find out the total Gini index. And then once we have that, then we choose we do this process for all of these individual features, and we choose that feature as a root node for which this Gini index is minimum. Here is again analysis. I will skip it for now. So the next algorithm I would discuss is random forest. The decision trees are easy to build, easy to use, easy to interpret, but they show high inaccuracy. Decision tree work great for training data, but not for unseen or test data. And this random forest combines simplicity of decision tree with flexibility and resulting in vast improvement in accuracy. As the term suggests, it is a forest, so it is a collection of trees, a lot of trees. So rather than earlier in the case of decision tree, we were dependent on only one single tree. Here we construct multiple trees, and then we pass our test data or the new input data to each of these tree, and ask the decision tree to ask all of these decision tree to classify them. Suppose we have 4 different class like A, B, C, D, and this decision tree results in class C, and this decision tree says that okay, the input data belongs to class D, and this decision tree says that okay, the new input data belongs to class B, and this decision tree says that okay, new input data belongs to class C. Then we go for the majority voting, and as you can see that okay, the class C appeared for 2 times. Then we say that okay, the final class is class C. Now the question is, how do we construct the random forest? So we start with creating a bootstrap data set. So suppose we have a original data set like this, where we have data for chest pain, good blood circulation, blocked arteries, weight, and heart disease. So to construct the bootstrap data set, what we do is to create a bootstrap data set that is the same size as the original, we just randomly select sample from the original data set. We randomly select these instances or data points from this data set, but the important detail that we are allowed to is that we are allowed to pick the same sample more than once. We can, in the bootstrap data set, we can pick up each of these data points more than once. So typically the selection or the picking up is done in such a way that 75% of the data is kept in this bootstrap data, and 25% we keep as test data. Once we do that, then okay, suppose we have randomly picked this data here, this data set here, then we will add it to our bootstrap data set. Then we again randomly chose any of out of these 4 data point. Suppose we picked up this data point as a random, and then we will add this to our bootstrap data set. We will do the same process. Suppose again the same data has been picked up, so we will add it to this bootstrap data set. So once we have that bootstrap database, we will create a decision tree using this bootstrap data set, but using only a random subset of variables or columns at each step. So earlier we were looking at all those 4 features to decide, okay, which one we should use as a root node or which one we should use as a next decision node. So now we will, in this case, we will in this example we will only consider 2 variables or 2 columns as each data set. So suppose we have decided that okay, and then once we have those two chosen, suppose we have chosen the chest pain and good blood circulation as two features that we want to consider, and then we would perform the we will find out the Gini index of these two features, and whichever is having less Gini index, we will use that feature as root node. So suppose in this case the good blood circulation came out with the minimum Gini index, so we have chosen that. Now we are left with 3 different features: chest pain, blocked arteries, and weight of the patient. Now again we will randomly pick 2 features out of these 3 features. Then we will, suppose we have chosen chest pain and blocked arteries, then we will find out the Gini index of these 2 features, and the same process we will do and decide which one should appear next here. So by this process we will create a decision tree like this. So here we have built a decision tree using a bootstrap data set, and such that only considering a random subset of the random subset of the variables at each step. So this is one decision tree we have created in this way. But we can create different kind of tree by repeating the process, because each time we repeat this process, different kind of different bootstrap data will be created and different variables will be chosen in the next step. So we can create a lot of other decision trees like this. So here I have shown only 6 such trees, but in practice we can have thousands of such trees. Then we use these trees to then we will supply the new input data to all of these trees, and then we see that okay, what is the outcome of these trees, and then we perform a majority voting for in among these trees, and we will decide the classification or the class of the new data point by looking at the majority voting results. So this is how we have done this. So here are the applications of these algorithms like logistic regression, KNN, SBM, support vector machine, random forest, decision tree. So you can look at them. So before I end this presentation, I would add one more slide. So there is we have to choose several hyperparameters when we perform our or train our model. So we can either go with a grid search or the random search. So suppose we have 2 different hyperparameters, we can make like this kind of a grid structured fashion, and we can go with the each combination of each of the combination. Each point represent here one set of hyperparameters, and we can go all of them by one, and we can also start picking up hyperparameters from this feature space or the hyperparameter space at a random. So I would highly recommend, or as this is a common recommendation, that you should go with a random search rather than grid search. So in conclusion, today we have looked at 8 of these very common and very basic algorithms that are commonly used in machine learning algorithms. And earlier when I started looking at these algorithms, I had a feeling by looking at these fancy names that okay, this is going to be a very different kind of field what I have studied till now. But later when I started reading about these algorithms, I found that these algorithms are quite intuitive. So I hope that after this presentation you also feel the same way, that these algorithms are quite intuitive, and next time you encounter any of these terms, you will not find them alien. So thank you for this, thank you for your attention. So I am open for the questions if you have any.